Okay, hello everyone. Thank you for having me and welcome to this talk. Catch me if you can, continuous delivery versus security assurance. So, before we get started, a bit of background about myself. So, my name is Abdessamad Temmar. I've started out as a penetration tester. I moved to Serious Advisory, which is French consulting firm based in Paris, where I work as an AppSec engineer. So for me, it was a huge change because instead of writing pen test report with vulnerabilities, I'm now helping dev teams to fix them. Uh, Still don't know how I felt for this, but I believe that defensive role can also be fun and more challenging. So my main job today is to help companies build an effective AppSec program, especially for those who are starting to shift their process to continuous integration, continuous delivery, and all this stuff. I'm also a WASP contributor to the community, so I had the opportunity to work on multiple projects like the OWASP proactive controls and the mobile security testing guide. Okay, so what this talk is all about. I will try to answer this question using the following animation. So first, we have modern, rapid, agile teams building and pushing their software to production. So for us, it's total chaos. And in the other side, we have attackers and attacking vectors and the evolving cyber threat that continue to be more and more dangerous and sophisticated. Basically, they are using the same tools and techniques for scanning their own scanners and hacking tools. And in the middle, it's every AppSec team or every AppSec engineer struggling and trying to keep up with both the velocity of change and the shifting threat of cyber attacks, which is quite complicated. So the main problem here is that as an AppSec teams, we still have under our belt traditional and legacy AppSec tool that fortunately doesn't fit anymore in this kind of situation. And most of the approaches I saw today is all about dumping existing legacy security tools into developers, which adds more complexity and frustration without solving the real problem. So these tools used to be useful in the past. I mean, for manual security assessment, for small scope and large release frequency, but it's not up to challenge anymore. And the existing legacy approaches just continue to be untenable as a way of working with modern teams. So in this talk, we are going to see how the existing legacy AppSec tooling must change or has already started to change in order to match the current trends and also keep up with the emerging threat of cyber attacks. So for automated security tools, we have different options. So in this talk, we are going to focus specifically on SaaS tools. We'll get to why SaaS is the best option. So I'm not going really into the other ones, but the point is there's a lot of options in the market and in the open source world. So running static analysis is quite simple. The only input we need here is the source code, and based on some detection and scanning rules, we run analysis in order to detect vulnerable code location that may lead to security issues. So it's quite simple, and this is basically why we will focus on this kind of analysis. So it is very easy to automate and operate, unlike the other techniques we mentioned in the previous slide. You can also run static analysis anytime you want for your dev cycle, and it can be also fast when configured correctly, which is very important in order to achieve continuous security scanning. And finally, the awesome thing about static analysis is it tends to point you right at the code that is the problem. And this is very convenient thing to have in a security tool. So I know some of you will complain about the fact that existing SaaS tools are prone to false positives, but we desperately need to figure out how to take benefit from such kind of tool, simply because it's our principal advantage against attackers. So unlike attackers, having the source code in our hands, we allow us to have full knowledge of our apps, so it's the only way to stay ahead of attackers. So in the markets and in the open source world, there is a lot of options. And in order to understand the difference between each kind of tool, we are going to try to solve the following problem using different tools category. So we are going to walk through quick and simple grep filters, then open source and commercial analyzers, to custom implementations. Okay, so this is just a made-up scenario, and it doesn't look like in any way of my previous experience in code review. So we have this external API which is vulnerable to path traversal vulnerability. So a path traversal attack, or we call it also directory traversal, happens when an external user can access through the application to files and directory that are stored outside the web root folder. So, and this problem occurs by manipulating HTTP forms inputs that reference files with, for example, dot// sequences and its variation, or simply by providing absolute file path directly, which allow you to access arbitrary files and directories stored on the file system, including the application source code itself, or even sensitive configuration system files. So in this case, this API is vulnerable when the search type parameter has path as a value. So for example, if I provide // etc/password as a value, I can download the password system file. So we also have a secure implementation to do the same thing. It's basically when we use file ID as a value for search type, where we associate IDs to files. So instead of providing the absolute path of a file to download it, we provide an ID, and then the application will try to match the ID with the corresponding path of the file stored on the server. And in this specific situation, we can't remove the vulnerable implementation simply because there is some other internal systems and heavy clients that are using it. So we are going to use static analysis in order to detect all the code location where we have the same problem and enforce the secure implementation in the future for our code base. So let's do it. So this is the target solution. So basically for each merge request, we will look into the changed files to detect if there is an insecure usage of our API. And then if it's so, we block the merge requests and trigger the alerts to our developer. So what is the success criteria in this particular situation? So first, we want accurate results. which means we want to avoid false positives as much as possible and avoid triggering false alert when scanning each pull request. And also, we don't want it to break the velocity of change and the deployment speed we already have. And finally, it must be something easy to implement, operate, and understand by each involved parties in this situation. So we can start off using regular expression. So first, we check out the code, we detect changed files, and then we grab the code to detect and save usage of the download file function. So this is a basic implementation, and I've saw many organizations relying only on regular expression and grep for code analysis, simply because it's easy to implement and a cheap solution. But it had some limitations. So the first one is we may have a lot of false positive. So first, we don't know the difference between comments, and also we can't make the difference between uses and definition. So in fact, it's really something super easy to begin with and operate, and it's also easy to understand the aim of each scanning rule just by looking at the regular expression behind each detection rule. But it has some limitation due to the fact that we can't make difference between calls and definitions or comments, and we can detect multi-line calls. And this is due to the fact that your code isn't a string, which what grep and regular expression are designed to operate on it. So in fact, it's a tree. So if you are using a compiler, the first stage is to build the intermediate code representation in form of a tree, or what we call AST, abstract syntax tree. Which brings us to the second technique, which is AST-based analysis. So before running code analysis, we start by building this tree, and instead of analyzing the code itself, we look into its AST representation. So this picture explains metaphorically the concept of AST-based analysis. So it's like we deconstruct a recipe into its parts, and it's the same thing we do with source code. We break it into pieces, or what we call tokens, and in the parsing stage, these tokens are then transformed into a tree structure that describes not only isolated pieces, but also the input code um, and their relationship to each other. At this point, we can make the difference between variable declarations, statements, expression, and so on. And then these tools have a bunch of rules. They run these rules against this AST representations in order to detect security issue. There is a lot of tools that operate at this level. For example, we have Bandit, which is a Ceph tool for Python code. We can use the core library to analyze and interact with the structure of an AST. In our case, the detection rule will look like this. So first we look for all instances of our function. Then we filter by the second parameter value equal to path to detect the insecure usage of our function. But the problem is, for each language, these tools or these kind of tools has a different way to represent the AST, which means that if your teams are writing code in different languages, and I guess this is almost the same case for everyone here, you have to learn, or you need to learn how the intermediate code representation looks like in order to write custom rules for each development language, which make it pretty hard to tune and maintain. And the second limitation is this is only structure analysis. This means we can't track where the input came from. So for the first parameter, we don't know where the data came from or by which means our API was called. To answer this question, commercial scanning tools have made available their own custom code representation on top of the ASC model. Like for example, data flow representation and with a unified language to interact with their own code representation. So let's focus on data flow representation. In data flow graph analysis, we collect runtime information about data in software while it's in a static state. And this can be achieved by using two concepts, sources and sinks. So sources are where the data is coming from. Basically, it can be attacker or untrustworthy input. And sinks are places where untrustworthy data can cause something bad or serious damage by forcing your application to behave in an unexpected way. Let's see quick example in order to understand these two concepts. So let's try to identify the sources here and the sinks. So for the sources, in this case, the sources are get request variables, and the thing here is pretty obvious, which is the system call to execute command. So in data flow analysis, we try to figure out how to connect sources to sinks. In other words, we try to identify code locations where it's dangerous if user-controlled inputs can get there. Let's go back to our initial problem again. So here is a pseudocode of a well-known commercial tool. I've changed a bit the syntax since it is vendor neutral talk. So basically most commercial tools, as I said before, have their own unified custom language to interact with the intermediate code representation for different coding languages. So first we use find interactive inputs to identify the sources, and then we search all calls of our dangerous method download file with path as a value, and then we use this magic function in order to connect the sources to sinks in order to identify vulnerable code location, which is the final result of this scanning rule. So yet this kind of tools have the ability to provide robust results with a unified query language to write custom rules for multiple languages, but unfortunately they have some downsides. First of all, they are too expensive, and that is the biggest barrier for a lot of team to getting started with them. But even if you invest in such tools, you will notice that they are pretty hard to tune simply because they are not designed to be open for end users. And this, what we saw basically in the previous example, as we don't have a full knowledge of how each functions operates. So writing custom rules can be a time-consuming task, and for AppSec teams with a limited resources and a large number of applications with different technology, this is not a good option. And another problem is the distance between concrete code and corresponding representations. So sometimes this is due to a mismatch in the parsers used by the tools itself being different from your build environment, which honestly can affect the final scanning results. So in my previous experience while using scanning products at some level, we noticed that during the continuous scans that some issues did disappear to reappear again without making any changes to the source code, which is quite funny. And another problem is not all dev languages have the same quality of rules and support. So most of commercial tools will say, yes, we have a support for all these languages, but they are only effective in the most used one, like Java or PHP, for example. But unfortunately, it's not always the case for other scripting languages like Python or even JavaScript. And another downside, they are too slow. So some vendor will say to you that we support incremental scan, which means scanning only the changed files, but the reality is that there is no big difference between this and full scan when it comes to heavy projects. And this is something I've personally noticed in one of the product used by my clients. So at this level, we saw simplistic grep combined with regex, but also complex advanced EST or data flow analysis. But we still don't have the perfect way to solve our initial problem. The good news is an in-between solution, which called SumGrab, that try to get the best of each solution we saw before. So it's an open source tool, and the original version of SumGrab was part of a large framework used by Facebook for code analysis, and it also have some good support for different languages, and more are coming. How SemGrep can solve our initial problem? The big advantage of SemGrep is it's very simple to write scanning rules. So if you go back again to our initial problem, we can use this pattern to detect insecure usage of our download function. So $x is what we call a meta variable to match the first input, and then the second part is easily detected by providing the same pattern. Okay, let's see now how we can use semgrep in order to execute this rule. In order to run semgrep, we have different possibilities. So we can either download the package, or we can use directly its Docker image, or we can use this web interface made available by Retail Corp, which allow you to run and test semgrep rules. So here we have our rule, and here you can put your test code. So after executing the rule, we will be able to match the insecure pattern. So unlike basic grep, we have the ability to make the difference between a call, comments, and multi-line calls, and also we can make the difference between a string and an actual call. So this is just a basic example, but we can see that SemGrep offer more options and flexibility than an ordinary grep. You can also check other examples available on the debugging web interface. So for example, we can use SemGrep in order to enforce best practices for API security, specifically in order to enforce security flags for user cookies. And there's also a nice feature called autofix, which allow you to automatically fix code and propose secure implementation based on your own security policy. Okay, so let's go back now to our presentation. So the first advantage of SameGrep is in terms of the execution speed, which is incredibly fast. And the second point is it is something easy to learn. There is even a tutorial on how to learn SameGrep in 5 minutes, simply because the syntax to write custom rules for a specific dev language is quite similar to the language itself. So if you are coding in Java, you can easily write rules for Java and so on. But the main limits of this solution, we can't track data over multiple files or trustworthy input over multiple files like what we did before with data flow analysis. So which one is the best option? The answer is it depends. But if you want to sum up all the functionalities of the tools we saw today, we have two main categories. So the first one is lightweight basic check, like using grep or its advanced version SamGrep. They are basically interesting when it comes to enforcing some security policy into your code base. For example, making sure that there is no usage of insecure crypto functions or something like the example we saw today. And in the other hand, we have AST or SafeG data flow complex check, which offer more robust code analysis capabilities, but it's very heavy and too expensive to maintain, and it's quite complicated when it comes to writing custom detection rules. So between these two solutions, and as an AppSec engineer with a limited time and resources, I think SameGrep is already enough. This doesn't mean that ESC based or complex check are not useful, but in my opinion, they are specially designed and can be useful for security researchers to detect complex stuff, for example, in open source projects. And this is basically the same thing we have with CodeQL, which is an open source engine analysis provided by GitHub to query large code bases to detect common security issues. But let's not forget about the main objective, which is writing secure code. So we were somehow blinded by this illusion that we can detect everything. But the reality is, and this is one of my favorite quotes of Clint Gibber, should follow him. He got some interesting stuff about the subject and AppSec in general. So the reality is bugs and issues will always exist, and forcing our tools to detect all of them will only bring too much complexity to the existing process and will lead us to this kind of situation where reports are only full of false positives. Instead, we can take advantage of modern secure frameworks that include by default protection against most common issues, and by using these frameworks it is more easier to detect deviation from secure code pattern than detecting bugs using the previous methods we saw before. So for example, in Angular, when used correctly, it can provide native protection against one of the most common security issue for web application, which is cross-site scripting, except the case when the parameter dangerously set inner HTML is enabled. So instead of writing complex EST or data flow analysis rules, we can simply grab the code to detect if such parameter is enabled inside the code, which brings us to a third option, which I believe is the future of AppSec. And I suggest you to check this awesome talk from Jim Manico called Advanced in Secure Coding Frameworks at AppSec California, which explain how we can solve the most critical issue that we have been facing for years by only using the technology and using secure by default frameworks in a transparent way for developers. Okay, I want to finish this talk with some thought about the future of AppSec. So, if we look at the evolution of computing over the last years, whenever one technology stopped improving, we replaced it with an even better one. For example, when we could no longer shrink our vacuum tubes, we replaced them with transistors and integrated circuits where electrons move around into dimension and so on. And I believe the same things go to SaaS tools. I mean, putting all our energy and research efforts on using complex ASC or even data flow based analysis won't make the situation better. But instead, by the adoption of secure by default frameworks and lightweight checks, we can provide fast feedback to developers about the security level of their code by spotting deviation from secure patterns. And I believe we are in the good direction in order to achieve this goal. So that's all. Thanks for watching. If you have any question, you can reach me out at my LinkedIn or my Twitter. I would love to hear your thought about this subject and specifically the future of AppSec and automated security testing.